Okay, all right. Some people probably still gonna pop in for the next couple minutes, but that's fine. We're just gonna be doing a little bit of a basic introduction. Welcome everyone to the first collab of the year since last year with ACM Cyber and QCSD, the quantum cryptography. For those of you on the ACM side and want the check-in code, it's ACM loves QCSD. And as we kind of give the little introduction, feel free to check in. Ooh, what is that white bar, Sean?
Are you? Oh, can you? I'm gonna, before I forget to check into my own event, I'm gonna check into my own event. So I'm on another window. That's why it probably looks weird.
Okay. Well, as you're doing that, I will give a little bit of an introduction on who. Oh, too far, Sean.
That, yeah.
Also, don't forget to do the slide sharing thing with me. So welcome everyone. I am Andy. I am the president of ACM Cyber, but I am also one of the logistics directors for QCSD. So I'm kind of playing both sides here. So I always end up on top. I am joined here by Ishan, who is also a part of QCSD, a former member of ACM Cyber,
Yes.
who actually, last time we gave this, was giving it on the ACM Cyber side.
And oh, how the turns have tabled.
Yes, our beloved Matthew was giving the QCSD side. So yes, oh, how the turntables turntable. Okay. Do you have anything more you'd like to say, Ishan?
Yeah, I'm external director for QCSD technically, or I'm supposed to be communicating with external organizations, but I also apparently do the logistics and the technical events.
Nice. All right. So I guess with introductions out of the way, if anyone shows up late and asks for the check-in code, I will have it posted. I can just quickly hit bam, enter. So all right, let's get started with the content. So before we even get into the quantum stuff, let's go a little bit over what encryption is and do some basic things about that. So first off, what are keys? Well, keys are pieces of information, almost always numbers, that we can use to encode and decode information that we want to transmit securely. So for example, say we wanted to encode the string hi. We tried to tell someone hi, but we don't want other people knowing we're saying hi to them. So we need to convert it into a number. There are many ways to do this. You can use ASCII and take that value, or you can use your own system, but we're just going to be using what position it is in the alphabet. HI, we're going to turn that into 8, 9. So our key in this case is 5. So we're turning 8, 9 into 40, 45 and encrypting it. Now, if you got that string out of nowhere, 40, 45, you wouldn't really know what it meant unless you had the key. If we know the key, then it's trivial to decode. You just divide it. But even if you didn't know the key, you could technically brute force your way to figure out what the message is by trying out all possible keys. So having a more secure key means that your information is encoded more securely. We can use keys in two different kinds of ways. We can use the same key to both encode our plaintext into the cipher and decode into the plaintext. That is what we just did before, using one number to multiply. Or we can use, that's called symmetric key encryption. Then there's asymmetric key encryption, where we use a different key to encode and decode. Typically, one would be a public key, which is the one that used to encode, and a private, no, excuse me, reverse that. And the private key, which we use also. So now we currently, most of the time, use RSA encryption. That is one of the more secure encryptions. That's what encodes, say, your banking information, stuff that goes across the internet, et cetera, et cetera. And it's based on the idea of you having two really big prime numbers. Now, we call those P and Q in this case. You multiply them together to get a really big number. We'll call this N. And the numbers are simplified in the diagram. But in that diagram, our product is 14. we use that product to generate our public key. And because we generate using that public key, we also need to generate our private key at the same time. Now you can generate the public key with n, but you can only generate the private key if you also have p and q. Now, since they're really, really big prime numbers, I'm talking huge, it's pretty secure. The basic flow of it would be simplified in the diagram. Say we have our message and that's encoded to 2. You bring that to some power, which is the public key. You bring it to the power of the public key, modulus, which just means remainder for those of you who don't know after dividing, modulus the n, the product. And that's our encrypted message. You send the encrypted message over using that same product, that same n. If you bring the number to your private key, you can reverse that and get the same message. Now, this is secure mostly because realistically, we're not able to factor these large prime numbers. They are huge and they would take enormously long amounts of time too. But in theory, quantum computers can do this really easily. So we've got something called Shor's algorithm, which was developed, and it provides quantum computers a way of factoring numbers a lot more efficiently. We've got the pseudocode up here, but to kind of summarize it, when you have the certain functions, you can, using a constant modulus, see a periodic behavior in it. And we included a graph of what that kind of looks like here. So what, in a sense, you're trying to do is you're trying to find the smallest number so that when you take the modulus, it equals 1. And that would be the points here, obviously with 0, but here and here and here. What it does is something that classical computers cannot do. It evaluates all points at once and uses the kind of qubits to find that lowest number. Now, I'm doing a bit of hand waving here because there is it's kind of a complex circuit, which involves some stuff that we're not going to be going over in this, but we will be going over it more in depth when we go to our KISKIT workshops. We'll be implementing them in one of those. So stick around if you are interested in actually implementing Shor's algorithm. But point being, with a quantum computer, it fundamentally breaks RSA. Now, RSA is asymmetric. Asymmetric is usually the safer option. However, when we get to the quantum key distribution, that is actually symmetric. So it's a bit backwards. One might think, oh, symmetric is less secure, but in this case, not so. Now, for those of you who are curious and know what this means, that's the time complexity for Shor's algorithm. It's kind of ugly. Usually you think like, oh yeah, O of n or O of log n or n log n. Nope, that is that beast. And the sieve method of the classical computing, which is at this point the most efficient method, doesn't look nicer either, but Shor's algorithm is pretty close to log n. So that's actually really efficient for factoring numbers. Now, I'll pass it off to Ishan for a little bit to talk about some of the basic quantum knowledge that you might need for this.
Yep, okay, that's me. Also, I mean, regarding the previous slide, for Shor's algorithm, we generally just say the time complexity is log n, just to simplify it. But anyway, I'm going to go a little bit into the quantum stuff that you need to know for this workshop. I'm not going to go into too much detail about it because it's not the focus of the workshop. If you are more curious about it, we do have like 3 intro to quantum computing workshops at this point already on our YouTube channel. So yeah. Okay. First thing you need to know is the idea of superposition. So in classical computing, you can see in that diagram on the bottom, you have bits, right? and those can either be a 0 or a 1. And you know that if you say write a bit to be 1, it's just going to stay like that until you rewrite it. And then when you read it again, you know it's going to be a 1. It's completely deterministic, right? A qubit works a bit differently. So actually, instead of only being in 2 states, the state of the qubit has to be described as a linear combination of the 0 state and the 1 state, if that makes sense. That's some linear algebra terms. But basically, if you look at that diagram, it's the position of that point can be anywhere on that sphere, if you want to think about it geometrically. And then when you make a measurement on the qubit, and I'll talk later about what a measurement means in the context of this workshop, when you make a measurement on it, it is going to, what you're going to read is that it will either be in the 0 state or the 1 state. So it will collapse to either of those 2 things. But unlike a classical computer, it's not deterministic. You don't actually know necessarily what it's going to collapse to before you make the measurements. Okay. Now, let's talk a little bit about light. So you might know that light is made of electromagnetic waves, right? So now these waves, it does its waving in a certain plane. So we could say it's polarized. So in this diagram over here, it basically has light that's polarized either vertically or horizontally like this. Now, what you can do with that, you can have this kind of filter that filters out, that only lets light through that is polarized in one direction. So you see this filter over there is only letting in the vertically polarized light. Now, why is this important? Well, going back to the superposition idea in a qubit, what you essentially have is you can have the photon be like a qubit. Its polarization direction is any of the states that it can be in. And the measurement you're making is when you put it through a filter and to see which direction it's polarized in. Okay. Okay, before we go forward, are there any questions on this?
Yeah, someone had a question about the ket notation.
Okay, ket notation. Yeah. I wouldn't worry about that right now. Ket notation, it's just in quantum physics, it's a way of representing the vector that is the 0 state or the 1 state.
Our president, whenever he gives the intro workshop, has a pretty good analogy, so I will use that. So it's like flipping a weighted coin. Your 1 and 0 are basically heads and tails. When Ishan had mentioned linear combination, that's like saying, okay, your alpha and your beta are your probability chances that you're going to get a heads or you're going to get a tails. It might not be 50-50. For a normal coin, it will be because it's fair. But in terms of qubits, we can use some quirks with the quantum particles, the qubits, to force them to be something that's nicer and make it not be as random. And we will get into that in just a second.
Yeah. Is there any more questions on that? Someone,
Yeah,
I think someone is raising their hand. Yeah.
Yeah, can you hear me?
Yes, I can hear you.
Okay. Yeah, I'm just wondering about the filter that you talk about.
Okay.
How does the speed of the way that it reads it compared to classic computers that we have today, like just reading the ones and zeros in binary?
Okay, that's a good question. I actually don't know the answer to that.
I don't think it's I think it's just like a really, really well-designed filter. Like you have polarized sunglasses that can polarize light. Like if you look at a TV and you turn your head to the side, all the light it'll just be a blank screen. I think it's just a really expensive version of that they used that essentially allows no light in the other ways. The detectors at the end, that's a hardware question. We're not super knowledgeable on hardware because it's not as easy to get a hold of.
Oh yeah. Essentially, it should be faster, right? Than just reading like a typical binary.
In theory.
I mean, maybe. I just don't know.
In theory, but we can't give you an answer for sure. Next time we give this workshop, though, we'll figure out beforehand.
Thank you.
Our president Ben is here. If he maybe knows the answer.
I'm not sure if I fully heard the question actually, but you asked about reading a qubit versus a classical bit.
Yeah, the speed, like if there's any less, because I understand like how having the qubit would make the computing power faster, but as far as like reading the state of it, it seems like it would be the same speed.
Yeah, I think maybe I get your question a little bit. So when we're talking about quantum computers being faster, at least my understanding of it is that fasterness, I guess, is not necessarily due to the operations being done faster. So like you can speed up, a regular computer, you can use, an optical chip or something like that instead of, silicon, for example. And that's going to make your actual, the speed of your computer itself faster. But quantum computing is faster in a different way. It's faster in that your calculations are kind of being done in a different fashion. So instead of doing calculations with ones and zeros, you're doing calculations with these qubit objects that Andy and Ishan were kind of explaining. So that's what's going to make it faster. In fact, I think it might even be the truth that quantum computing itself is not even necessarily faster. The actual processes might even be slower, but it's the nature of how you're doing these operations that's going to make it faster. So Shor's algorithm, for example, you're not running a classical algorithm, right? And that's not what's making it faster. It's just that you're able to manipulate these properties, these quantum properties, to make it faster. So I'm not sure if that fully answered it, but
quantum computing allows it to be more efficient because you can, rather than going number by number to try and find the period, you can essentially look at all of them at once and position your qubits so that it gives you a really, really good guess. Now, obviously, error correction is a big thing in quantum computing right now. So you're not always certain that the answer is right. It might be slightly off because, a highway 3 miles away was rumbling and it affected the quantumness of the of the chips, or it's screwed with something. But you have a pretty good guess in a more efficient way.
I see. So is it like a more probabilistic method of calculating then?
Yes.
Computing?
Exactly.
I see.
But you can use the properties of quantum physics to your advantage to make those probabilities less random and more deterministic. But yes, any other questions?
Yeah.
All right. I will.
Okay.
I guess it does in a
about
sense parallelize the computation. Right, Ishan?
I would hesitate to say that it's equivalent to parallelization.
Maybe not equivalent, but it's a sort of a good analog, because I guess in Shor's algorithm, it is definitely essentially kind of parallelizing the analysis, but not parallelizing the computations. It's a little bit more complex than that. All right.
Okay.
All right. Before we go on, do we have any other questions?
Yes. These are good questions because this is a difficult topic and
Yes.
secret. We don't understand it either.
Yes. This is just a facade. Okay. So yeah, I'll take over for a brief second. So now that we've got our polarized light, what can we do with it? Well, if we wanted to use this in a way that sort of mimics our bit system, we can take our polarized light and put it back through a filter. Now, if we take our diagonal light and put it through a diagonal filter, theoretically, all of that light, because it's polarized in the same way, will pass through it. Whereas if it were polarized in the opposite direction, none of it will come through. So that gives us a 1 and a 0 state. The same thing happens if we have a vertical or horizontal filter. If we put vertical light through a vertical filter, we get a 1, and horizontal light through a vertical filter, we would get a 0. Now, I have a, did it move forward? I have a question for you all. I will open up the poll. What do you think would happen if we put vertically polarized light through a diagonal filter and diagonal through a vertical filter? I'll give y'all a brief moment to answer that. Okay. Whoever just answered, good job. Two people got it right. Okay. Seems like most of you are getting it right. One person didn't, but that's fine. All right, I'm gonna close the poll. So yes, for the majority of you, 50% for both 1 and 0. Ishan, would you like to explain why? Ishan?
Yeah, okay, I know I had to unmute myself. Yeah, so basically going back to the idea of the qubit being able to be in a state that is not just 1 and not just 0 when we're not observing it. What you're essentially doing here is, let's say that the qubit is in, so let's say the photon is vertical, but instead of measuring it in either a vertical or a horizontal filter, you're measuring it in a diagonal filter, right? What you're essentially doing is you're measuring it in a different basis than what it was initially in. And so when you measure it, it's still got to collapse to either one of those two states, 0 or 1. But this time your 0 or 1 is off to the side, if that makes sense. It's diagonal. So it's going to give you an answer. And it's going to do that with a probability that depends on the angle of the filter. So like a perfectly diagonal filter, we're talking 50% 1 and a 50% chance of it being 0. If the filter is tilted closer to being vertical, you're going to have a greater chance of it measuring that 1 because it's closer to the orientation of the I guess it's closer to the basis of the photon.
And that goes back to the this thingy right here. So with that analogy that I brought up of the coin, when you are diagonal here, you have a 50% chance of it being 1, 50% chance of it being 0. But, or wait, not diagonal, that would be horizontal, right, Ishan? Horizontal is 50-50? Yeah. But as you go up or as you go down, you are getting closer to a probability of it being a 0 or closer to a probability of it being a 1. And that is directly analogous to these filters, where the more you tilt it, the higher probability that it's going to be a 1, higher probability that's going to be a 0, et cetera, et cetera. Now, next, we're going to be giving a kind of demonstration on the actual application of this and what it looks like. Do we have any questions before we go on about any of the prior knowledge that we've been talking about? Yes, Ishan?
I don't see anyone.
Applying
wait,
a new
no, someone
filter
said
is
something.
equivalent to changing the basis of vector space.
That's a good question.
Ben,
I would.
do you have anything to say about that?
Is Ben here?
Sorry, guys, I was in a loud spot for a second. That is a fantastic question. I believe the answer is that's essentially it. Applying a filter would actually be the equivalent of like taking a measurement. So if I have a single photon, that photon can only have one polarization state. But if I pass it through a filter, so I guess here would be your example. Like, let's say you take a diagonal photon, right? So that diagonal photon is some combination of horizontal and vertical. When you pass that diagonal photon through, let's say, a vertical filter, right? That's going to be the equivalent of taking a measurement, right? Because you're forcing that photon to choose. You're forcing it to either go through as a vertical photon, or you're forcing it to decide it wants to be horizontal and not go through. So that's what we'd be saying, like the wave function's collapsing. So that's I think on the intro workshop I talked about like Schrodinger's cat, right? When you open that box, that's kind of what that would be. But passing it through that filter is also going to affect your basis as well, right? If you pass vertical light through a diagonal filter, it's now going to put that vertical light into that kind of diagonal basis. So it's a subtle point. I'm not sure if we can fully explain it in the workshop, but I think that's maybe doing my best to try and explain it. Does that help?
Awesome. So to stay on top of time, we are going to move on, but if you have any questions, we're going to have a Q&A at the end. So pin those questions for the moment. So like I mentioned, we're going to show you how it all comes together. I've pasted the link in chat to a Google Collab that we have. We will also be sharing it on here, but if you are interested in seeing the code afterwards or going along as we do, then feel free to go there as well.
Right. So we're going to have a demonstration now. So the question we still have is, okay, so we have quantum computers, or in this theoretical scenario, we have the tools to be able to use them. How do we ensure secure communication with what we know? That is a process called quantum key distribution. What's happening is, you can see by this diagram. So we have Aaron and Sharon who are trying to communicate with each other, right? They need to be encrypted because eavesdroppers like Hackerman over here want to hear what they're saying. And so to encrypt it, they both need to have a key. Now this is going to be a symmetric encryption scheme. So both Aaron and Sharon need to have the same key. The question is, how are they going to give the key to each other without it being possibly intercepted by the eavesdropper? And that's where this comes in. Ignore that. That's just installing some dependencies.
So those
importing.
dependencies right there, we're using KISKIT. For those of you who know and those of you who don't know, this is a library in Python from IBM, which is kind of the industry standard for interfacing and sort of simulating what quantum computation would be like. If you are interested in learning more about that, stay tuned for our KISKIT workshop series.
Right. Okay. This over here, okay. I didn't change the names here because this demonstration still uses Alice and Bob. But here, yeah, I'll just use Alice and Bob. So Alice, this is just a method to encode Alice's message. Don't think too much about it. What's basically going to happen is the message is going to be a string of zeros and ones now. And that's all that is. Okay, so what they want to do, Aaron, aka Alice, I know it's weird, wants to send their key to Bob/Sharon. I should have changed these names before. And so they need to send that string of digits across. And then what's going to happen is Sharon over here is going to measure each of those photons that Aaron sends across. And it's going to get either a 0 or a 1. The same with over here. And this is just a function to do that. Now, the key here is actually Aaron will be sending zeros and ones in the form of photons that are vertically polarized and vertically, horizontally, and diagonally polarized in both directions. And Sharon is actually not supposed to know which filter to use on each photon. When she measures the photons that are sent over, she's going to make a guess on which filter to use on each photon. So as you can see here, she uses a vertical filter on a vertically polarized photon. She's going to get a 1. That last one over there uses a diagonal filter on a diagonal photon, and since the way I drew it, that is going to get a 0. That middle one, however, she used a vertical filter to measure a diagonal photon. She is going to get either a 1 or a 0 with a 50-50 chance, as we saw earlier. The discard thing, I'll get back to that later. So Aaron's going to send across all his photons. Sharon's going to make guesses on the filters and measure those photons. Now what they're going to do, Aaron knows which filters he used on the photons. He is going to share that list with Sharon. And then what Sharon is going to say is, okay, well, I guessed these ones right. I did not guess these ones right. The ones she did not guess right, she's going to discard. They're both going to discard those wrongly guessed photons. And then what they're going to have left is the photons that they did have match. So in this case, we discard these ones. The final string is going to be 1, 0, 0. Now it's actually okay that Aaron is sharing the which filters he used across to Sharon, as we'll get to later, because even if the bad guy intercepts that list, that is useless to them unless they also intercepted every single photon. And as we'll get to later, there's a problem for the bad guy if they try to intercept every single photon. Okay. Yeah, and this method right here, it's just gonna discard the incorrectly guessed bits. And I'll get back to this method a little later, but basically what this is this is a method that Aaron and Sharon can use to make sure that actually no one intercepted their photons. And again, I'll talk about that later. So this then would be the entire algorithm. Alice generates her bits, and then she records which bases they're measured in, aka which filters. And then Bob over here on the other end is going to decide which filters to measure in. Okay, this just prints those out. Or actually, yeah, what happens is now they've sent those across, and now they're comparing it, and then they remove the bad guesses, and then just to print them out over here, these were the results. So in the end, what they have after they communicated their digits with each other, after discarding the bad ones, they each have this key. As you can see, they are the same key, or they should be. Yes, they are. That would have been embarrassing if they weren't. Okay, and it says, yeah, the samples do match each other. All right, these are their whole keys. Okay, so that seems to have worked, right? They sent across, so Alice sent across her bits, and then Bob, upon receiving it, and they're now able to find their common digits. And so now they have the same key. Before I move on, are there any questions on that?
Now this is very complex. So if we lost you guys anywhere, let us know and we can go back and explain it a little bit more in depth.
So is what they're actually sending, so they're just sending like randomized light, or are they sending like a specific the specific pattern of light, and then the filter is receiving that based on the key?
It is, yeah, so it is best for it to be randomized.
Okay.
Because well, not just in quantum cryptography, but in any sort of encryption scheme, you want your key to be as random as possible. So yes, ideally Alice is sending over a random string of digits, string of zeros and ones, in the form of photons, which are also randomly polarized in either the horizontal direction or the diagonal direction.
And a note on randomness, you can use quantum computers to generate truly random numbers. And we'll be doing that in our KISKIT workshop coming soon, trademark. So if you're interested in making a random number generator with a quantum computer, stay tuned.
Yeah. And so basically what the point of this is that now both parties have a key that each of them didn't directly send over, if that makes sense. And now, okay, I'm going to move on now. There is a malicious party here, right? The hacker man who wants to intercept the keys. And let's assume that they can do this. Let's assume that they can intercept every single photon and also intercept the filters that Aaron used. So because this happens, what's actually going to happen? So as Aaron is sending across the photons, the hacker man also does not know which filters he used. The hacker man is also going to have to guess which filters Aaron has used. And what this means is they're going to make some wrong guesses. Like for example here, Aaron has sent across a diagonally polarized photon and the interceptor measures it with a vertical filter. That's going to cause the photon to collapse to either a 0 or a 1, and it will no longer be diagonally polarized. It's going to be vertically polarized now as it gets sent to Sharon. This is important now because this now means that if Sharon tried to read that with the diagonal filter, it's no longer going to read as a 0 or a 1 with 100% chance. Now it's going to read as a 0 or a 1 with a 50% chance each. And that changes things. Here's what that changes. So we have this next code snippet here, which also has the interception aspect over here. This interception aspect essentially changes a bunch of the photons that go through to the other side. And so what Alice and Bob are going to find are that when they try to communicate that with each other, and then they discard what they think are the bad bits, they're going to take a small sample of what they have left, compare it with each other, and it's not going to match up, as you can see here. That is a direct result of the interceptors tampering. So now that they know their keys don't actually match, they know someone messed with them. They know someone was trying to read their key in transit. So they know their communication is not safe anymore. They can try again somehow. And the interceptor will not have gained anything because now they have a key which actually doesn't even match either of these, and Alice and Bob are not going to use that anyway. So yeah, as you can see, they're both false. And yeah, that is the theoretical idea behind quantum key distribution. What makes it secure? You can transmit the key to someone else and automatically know if it has been tampered with or read. Okay, I see there were some questions in the chat.
Ben answered one of them. I don't think there were any other ones unless they were DM'd to you.
No, none were DM'd to me.
All right.
Yeah, so okay. Yeah, Ben answered that one question. Will the orientation be disturbed if HackerMan measures it? And yes, like Ben said, it depends. If the HackerMan gets lucky and just happens to measured with the right filter, then there wouldn't be any way to tell if that one was messed with. However, keys are going to be really long strings of digits, right? You saw in RSA encryption, they have to be really big numbers. Same idea with this. They're going to be really big, and it's going to be basically statistically impossible for the hacker man to have correctly guessed every single filter.
So when it sends the light and it's filtered, is it, because it's a probability, is it sending like a large number of particles that are then on average correct, like it would converge to the correct filter, to like the true average of what the filter is finding or is looking for?
Not sure what the question is.
I guess so. Is it just reading like one particle that it's sending?
Yeah,
or
yeah.
is
One particle. So
okay.
one photon, one measurement. So like one photon at a time. Think of it like that.
Oh, I see. So what happens if it just like, if it's diagonal, but like it's because it's a 50-50 chance, the key doesn't work out, it doesn't read the correct binary string that it's looking for?
Yeah, so that is, are we assuming no interception?
Yeah, assuming no interception,
okay.
But it just
Yeah, so
isn't correct.
That's what's going on here. After Aaron sends over all of the photons, they're going to compare which filters they used, and then discard the ones that were wrong guesses on Sharon's side. So for example, that second photon over there, that is a vertically polarized one. Sharon guessed and used a diagonal filter, which it shouldn't have been, so they're going to discard that. But at the end, they are both going to have a string of digits that are the same for both of them.
Okay, so
That
like
makes
for
sense.
example, where it's discarding, where it's diagonal but it's supposed to be vertical, that would that discard every time, or would that discard 50% of the time?
No, so what happens is they'll discard it every time, because they're just going to say, oh, I used the wrong filter here. It doesn't matter what digit was read. It could be a 0 or a 1. It was just the wrong filter was used, so we're not going to use this digit.
Oh, I see. Thanks.
Okay, someone asked. Yeah, okay. Andy answered that in the chat. This is basically the end of our workshop, by the way. So
Yeah, pretty much from here on
if you
out.
want to keep
there's a
answering
Q&A
questions.
session. But
Yeah.
before we do, like to just go to the slideshow, like present. We do have a GBM coming up this Friday, on January 15th at what time again? I forgot to put the time.
Should be 4 to 5.
And I've got a poll about it. So are y'all going to our GBM this Friday? I got one yes. Hey, everyone's going.
Hey, this poll seems rigged.
The game was
I
rigged
don't
from
know
the
what you're
start.
talking about.
One person couldn't bother answering or didn't want to enter the poll so badly they just left. That's cheating the system. But okay. Yes, so this Friday, January 15th, is our GBM. You can learn about what we've got up for the rest of the quarter, and as including a hackathon that we're likely going to be doing, signups for that, the MIT IQ hack, right, Ishan?
Yes, I can.
As well as we'll be sending out our staff applications. So if you are interested in becoming a part of, helping out with QCSD, yeah, be sure to be on the lookout for that. I've got nothing to push for ACM Cyber, but we do have this recording will be on YouTube. We'll post it onto both the ACM Cyber and the QCSD Discords. And it'll be on the ACM, I don't know if it'll be on the ACM or the QCSD, but regardless, the recording will be posted on Discord. But the next event for ACM Cyber is next week on around the same time. Will be our introduction to CTFs, I believe. So be on the lookout for that. So if you want to stay connected with us, right side is all of the QCSD socials, left side is all of the ACM Cybers. And I will stop the recording. Thank you for those of you who are watching this online. And thank you for everyone who is here. If you don't have any questions, or if you're not interested in hearing other people's questions, this is the end. Thank you.